Welcome to our second live coding with Alan Calvitti. He's going to talk about functional data flow. Alan, everything is yours. Please go ahead.
Oh, thank you very much, Mads. Thank you, everybody, for joining. This is the second session in our live coding data science sort of series. And we started off by looking at this at a specific data challenge called the Explainable Machine Learning Challenge. And I will go into part two because we did not finish with that. I'll definitely take about half of the session or so to do this. But before we get into that, I thought I would do something because we've had some requests that we didn't do enough live coding. And I think that that's right. And so I'd like to do something with a simpler data set. In fact, it's a toy data set to illustrate a new function that I've added to my toolkit. If you remember last time, for those who were here last time, I actually have a toolkit that is going to be bundled up with my book, which I think is one of the most important things that is part of my book, because the book is about a specific data sort of study that we did, a long-term study at the Veterans Administration. But the functions that I've added to make this work out were actually much more general, and I wound up using them in many other subsequent projects. And I find it really interesting that you can do these sort of one-liners, and you can keep adding. As you can see, I have maybe 100 sort of very generic functions that I keep adding on, and they're all about manipulating data, whether it's tabular data or hierarchies and so on. And they're very generic sort of functions that I hope that at some point will become part of the language. So this is the latest one that I've added. It's called replace index. So let me just discuss that for about 15 minutes, and I think that people will get the idea of why these kinds of patterns are so important and so powerful within the language that are very difficult to do with some of these other data mining languages out there. So the idea was that I'm working on a new project that involves log analysis. And I've created an example log, and I'm showing it to you here. I've saved it, and I'm importing it. And it's basically consists of 5 sessions, number 0 through 1. So if we look at one session, it's very simplistic. I'm going to normalize it here. And you see that it's essentially just a sequence of events. In this case, they're generated by a device. So there are 5 sessions with, let's say, a mobile device, like a phone. And the different items here consist of screens, web services that are called from the device, and events that are generated by the code itself, by the device itself. So these are all logged, and they're saved. And you want to do some log analysis with these. And the idea was that we saw that some of the sessions were longer than others, and essentially wanted to have some function that is similar to map indexed, but it allows you to enumerate things in a way that would normalize by the length of the log. So if you look at this particular, let me make this a little bigger. This particular log has something like 20 different entries in it, but if you look at log number 2, there's fewer entries. I'll again normalize here. And if you do something like map index, I have a function called enumerate, which essentially uses map index to do this replace. Okay, so if I take this log and I enumerate it, since it's just a list, you see that essentially I've striped or indexed this data, and each one is a pair of, it's still inside of a data set, so I can keep normalizing this. You can see that it essentially just added the index number or position as a new item and prepended it to that, okay? However, map index doesn't have a way, as far as I know, to take the length into account, right? So for example, if this item in the log has 20 items, I essentially want to do things like enumerate it, but only go from 0 to 1. And put fractional numbers in between them. So I created this function called replace index. And this function essentially combines, first of all, it's a query. It's not really defined as a function. You can see that it's a query here. And it's going to illustrate several things. So first of all, it's a combination of map indexed and also replace is going to use them. But primarily, I want to illustrate that you can use query to great effect into here. So how do I write this? First of all, how does it work? So if I take this example log here, number 2, and do replace indexed. Let's see here, and you provide a rule. So this is an operator, right? So essentially, we can provide a rule here. The rule here should be in a particular format so that we can pass both the data and the dimensions. And to do that, the query begins by passing the identity and the dimensions here, okay? So the rules should be something like this. Let me see if I can fetch it here. Before I show you that, I'm going to show you just a couple of tricks of how you can sort of override data set's tendency to not show all the items. So if you can see here, this is wrapped inside of a data set, and you can see that the items are there, but they're not displayed. except for the very short ones, right? So you can do several things here. You can say, and I'm sorry that I'm not actually live coding it, but this is pretty simple, right? You take the example log and you apply short to it, and now you can see that most of them actually show up using the shorthand, except for the first one. You can use framed, and you can make even the frame kind of invisible if you want to by making it white or gray or something like that. This all seems to work for most of them, but not the first one again. Or you can wrap it, and I think this is the preferred method. You can just wrap each individual list into a data set in itself, and you can see that this worked for all of the different items. Okay, so these are just several different rules to make that happen. Okay, so if I add this replace, go back to the example here. If I have this example log here, I'm going to define this function which is called enumerate reverse, and I'll show you how that works. But basically, you can see that it uses replace index with a particular rule. Unlike map index, in which you have access to the slot notation, in map index you use things like 1 and then 2, and then you have to fetch the parts. I really don't like that anonymous aspect of it, so I prefer like these rules and pattern replacement. So enumerate reverse essentially works like this. If I do this, it should work directly here. Okay, now you can see that I took this log and it starts off with 19 and goes down to 0. And the rule, because there's a specific rule here that takes into advantage of the length being the first element of the dimension of this list here. But I can do more than that, right? So for example, like I said, like if you add this one, and of course, one of the greatest thing about Mathematica is just you can just take that slice that you just worked on and replace it with all, and all of a sudden you have the same function that is automatically applied to all the branches. And again, I challenge people to do this in Python, because basically you have to write these nested in what are called comprehensions, and they become exponentially more difficult the more layers of data you have. In this case, the data is simple, but by using this is just a fantastic sort of shortcut to make things, to basically just work on just the things that you want to at first, and then scale up your query. All right, so here's another example, and this is really what I was aiming at. I created another enumerate, which is called enumerate unit interval, which again uses replace index, but with a different rule. And this rule essentially is just saying, take the position, which is provided by map index itself, but divided by the normalized length. So essentially, this is going to map these to 0 to 1 to essentially, let's see here if it works. If I just do it on one of them, you can see now that I've striped it, but instead of the index going like 1, 2, 3, 4 or backwards, I'm essentially just taking this pattern and mapping it through so that the index just goes from 0 to 1. Okay, so and of course these are fractions. It's very easy to amend the rule to map this to, for example, I believe if I can just do this, you can just make it into floating point. If I just do this temporarily, not a big deal, but yeah, so okay. So in other words, I would just use this directly. I wouldn't necessarily even call these and name them, but I would just use replace index and provide the rule. So anyway, so this is something that I think I'm going to be using a lot, because this problem comes up in a lot of different situations where you have these logs that have different lengths. And now the actual challenge is to do some sort of like graph display of these, or even let's say like you want to look at these items as a function of time, but now you want to sort of like merge them together. And of course, if you just do them raw, they're going to come up with different. You're going to have different lengths, so you're not going to be able to compare. For example, when does a screen occur? Does a screen? The actual question would be: does screen number 3, does that occur? Does it tend to occur at the beginning of a log, or towards the end of a log, or in the middle, or of the session? Well, in order to combine all the different sessions and average them, you essentially first have to normalize them. And this is basically what happens here. So I'm going to show you. I'm going to do a live coding of how I actually use the example to essentially visualize this. So let's start with an example log here. I'll delete this. So we'll start with log number 1. And now I'm going to do something to essentially turn these, because they're given to us as strings. Let's just imagine that the log is given to us as strings like here. And essentially, I'm going to do something like here. And again, I've shown this before, but I think this is so powerful. When you don't know the level, if you're dealing with multiple levels and you don't know what level this particular portion of the query is acting on, use something like frame and you will see this immediately. Okay, I think this is something that can only be enjoyed with symbolic languages. You know, it's very difficult to combine these multimedia aspects. In other words, graphics and the textual output in a single, in the same sort of output. Pandas cannot really do this correctly. So Python, you can just hack at it. You cannot really do this really well. So you can see this. Again, let me normalize it here. Okay, so what we want to do is split, for each one of these sections, we're going to split each of these so that we can just plot the y-axis and just forget about the prefix, which is like screen or and so on, right? So how do you do it? Well, again, you can just use this pipeline. You use, for example, like string split. And I've already discussed, and I think this is very popular now, this operator that essentially is a position-coded query. So you can apply this to you can turn any function into an operator simply by placing it there, right? So this essentially splits it into two. Oh, sorry, this doesn't work out. Let me see if this, what are the heads of these? So all of these things are strings. Normal. Let's see here. If you do something like friend, string, oops, of course that's not going to work. Okay, there you go. I think I'll probably just typed it. So we're using the separator as the equal sign, right? So of course, just by using the string split, we've now like split them into, and now we're just going to map the second component, which is still a string, into an expression. In other words, an integer. So to do that, we'll grab the last component of each one of these, okay, and then map this to expression because these are still strings at this point. Okay, so now that there are two expression, now this is when I'm going to apply the enumerate unit interval so that each one of these sessions is going to get normalized so that you can, the position is going to be coded to 0 and 1. Enumerate. Oh, okay, so here's the problem. So this enumerate unit interval, so why didn't this work here? Because I forgot to wrap this entire expression into a query. So this entire thing has to be into a subquery. And I'll show you why. Because if you do this, you can see that this wouldn't work. Like you can't apply this enumerate into an individual number, right? However, if one wraps the query into this entire subquery, now the frame will occur at the level of the list, and this is at the level. So this is a good error to show people that enumerate. So I think that this is one of the big problems is that people don't know to do this. Yeah, people don't know to wrap and create like a sub level. And then everything after this pipeline component will actually act at this level here, at the level where the all is, okay? And there's a little bit of technicalities in terms of can I just put the enumerate directly into here, as opposed to that has to do with ascending versus descending operator. So the order in which you do it matters. For this particular operation, it worked, but sometimes you have to filter out delete missings and things like that. And so sometimes you actually have to do this post facto. So let's just preserve it the way that I did it before. But it gives you some flexibility in doing that. So, okay, so the enumerate is the standard way of doing it that you could have, that again, it's just, enumerate just uses map indexed, not the query version of that. But enumerate unit interval, now you see that it maps these into from the first, in other words, like the first item in the log goes to position 0, and the last item goes to position 1, and everything else is fractional in between. Okay, so once that's done, now I want to do things like delete missing because, for example, session 3 failed. Why did it fail? Well, it only had one item, I think, in it. So, of course, you can try to treat it, and I'll leave that for homework, but for now, I'll just do like a delete missing. Okay, so session 3 now has been completely dropped out. So again, this is part of a query, right? This is just basically taking the entire pipeline and building it on top of everything, including this the first all here, right? So this is a way to sort of wrap your brains around the fact that this works at level 1, this query works at level 2, and this particular query with a string or subquery works at level 3. Okay, so I believe that this section is okay. So if we try to do list join, this is actually a problem. Well, it will work, but it's actually incorrect from a statistics point of view because what you did was these are living in the same space. And this is something where you have to have domain expertise into what do these things really mean, right? You're not going to go into a problem cold as a data scientist. You have to know that what is S, what is E, and what is W. In this case, they mean they're masked entities. Obviously, we couldn't divulge the real data, but basically the screens, the events, and the web services are coded to the same numbers from 0 to, like, let's say 100 or 200. And therefore, you cannot combine them together. By doing this string split, you essentially have thrown out whether they are S, E's, or W's, and therefore they all get mushed together into the same space. So this is an error. Okay, the correct way of doing it is to first group it by the prefix. And the way to do that is, let's just start from, let's say, this point here. And we're going a little bit over time, but that's okay. I think this is really worthwhile as a lesson. So what you want to do is essentially just say, let's take one slice of this one. Okay, now we can do a group by. The way that group by is one of the most powerful operators in science in general. Of course, it comes from SQL. It's in many other languages, pretty much every other language that uses data. But there's some nifty features in the WL because you can manipulate things on a much more granular level. So group by allows you to do things like this. Let's say we want to group by first. And first would be the first component of this pair. By doing that, of course, we create this, and the second components are still there. Excuse me, the first and second component are still there. So the language allows actually this option where you could subsequently treat what happens in the value part. So you've generated keys by doing the group by first. And again, first meaning the first component of the pair, like, for example, S3, right? Oops. So you have S3. What we did, we said, like, group everything by the S. So you can see that we got a bunch of S's and E's and W's. And by the way, let me just show you before I go next. You can, again, typically how you work is you start on a slice of data, but then you scale it up to all, right? And you can see that it worked for pretty much all of them. Now, of course, if one particular session only has S's, then you will only see S. It's not going to show you E and W because they aren't there. This causes problems sometimes when you try to merge things and you get missing values. So that's something to be treated like later. But the thing that I really want to show is, let's go back to the one slice here, one slice of data, is the Wolfram language enables you to treat the, let's see if I can do this, framed. Okay, so if I've grouped these, but now you can see that if you can, the second part of the function actually shows you what happens to the value. So this is the key part of the group by, and this is the value. So in the values, we can basically take the last component. So really, this cleans it up a lot, right? So you basically are at the similar stage that we were before, but now we've segregated these, and now we want to do the plot bys separately for each one of these. So now that we've done that, so let's see this thing. These are still strings here, so we'll still have to do like toExpression. And actually, you can do this directly inside of here, right? Expression. So they're still there, and now we have to jump back out to do a query. We can no longer do if we do a query inside of here, what would happen? We're in the same situation where we missed before, where we cannot apply the enumerate unit interval directly here because it's one level too deep, right? This acts at the level of the individual items here. So we have to jump out of this subquery and go to the next level down. So how do we do that? So, okay, so let's try it here. What would happen if we do framed here? Well, here it's too low, right? Here you can see that we're trying to apply something and we cannot apply this enumerate unit interval because it would be acting at the level of all the three types of items that are in the log, S, W, and E. So instead, we're going to jump it up. So again, now you're scaling it up. And now this is the correct way to do it. So you can see, so I actually do this in a day-to-day. During my work, I actually use frame a lot just to situate yourself and find out what, it's a very handy tool to have that. Okay, so back to enumerate. So now we're kind of back to where we were before. We're enumerating it. So now each one of the E's, let's just look at one slice here. So for session 0, for example, we have all the S's. The S's are enumerated correctly from 0 to 1. The E's are enumerated correctly. And of course, now there is actually a bug here, a subtle bug here. Okay, so, okay, that's actually a good homework problem. But let me finish it. So in other words, this is actually also an error. All right, so now if we want to apply the list plot, so we can apply the delete missing because there's a delete missing issue here. And I think that's case number 3 again. Okay, so the same as before. Actually, make this a little bit bigger here. Okay, so now where to apply the plots? Okay, so let's try this. Let's try framed. And you can see that the third level is where we would want to apply it. So again, very handy way of sort of like showing what you want to apply. So now we're safe. We know that we can apply list plot here. List plot. Let's just do it randomly here without any options. Okay, we want to list join. So let's use the curry position curry operator again. So it's just joined. True. Okay, I'm not going to get into the other options, but you can see that you can just add as many options as you want. Okay, so as I'm writing this, I've noticed that there's another mistake here, a logic error, which is that once we grouped by the items, now these items actually there are different there's a different count of the S's, E's, and W's for each one of the sessions, right? So for example, S now, by using this enumerate unit interval through all of these, this is going to essentially say, well, there's only like 5 screens that we went through in this particular session 0. And there are something like 6 events, and there are 23 web services that were called in this session. So by doing enumerate unit interval blindly, this is actually, this is not correct, because we would be enumerating, the original intention was to enumerate when the screens happen at the beginning of the session versus towards the end of the session. However, by splitting it up into the SE and W separately, you can see that I will be enumerating only 5 things. So only 5 things would happen here. So you don't actually know whether the 4 is happening at the beginning or the middle or the end, because this is only looking at the screens. Whereas originally all these were mixed together, and we really the original intention was to actually just enumerate them as if they're all sort of like the same, essentially just count them as items. So we're kind of like stuck in this limbo where we know that the first case was a mistake because we did not separate them, and the Y values cannot be commingled. On the other hand, we cannot use this enumerate unit interval blindly, because then like these things are going to go out of sync. And what we really want basically, I think, is to enumerate unit interval and then split them before using the or plotting them on list plot. So let's just leave it up as homework, because we're already taking up about 20 minutes or more of this. But this is, I think, is got a good homework, and I think you just have to rearrange the order in which you do this. So I think it's something you start off with this. This probably is correct. Then you do the group bys, and then you do the list plot, and I think that will solve the problem. Okay. So again, when you do data science, typically you find these logic errors as you develop your code. And I think that what's ideal about the Wolfram language is that it's very easy to back out. Right, when you only have 3 lines of code, it's very easy to modify. Whereas if you have like 10 lines of code or 15 lines of code, it's a lot more difficult to do this. And again, Python as a simple example. Okay, so by the way, somebody's mentioning that they're not getting audio, so I hope that everybody can hear me. Somebody can double check that.
Oh yes, everything's fine.
Okay, good. Okay, so I think that's all I wanted to show you here. But let me just show you in the real case scenario. I'm not going to live code it, but basically, here's what happens in a real case scenario. We have, let's say, account identifiers. We have session numbers
sorry
here.
Sorry to interrupt you, Alan. Just a quick question about the homeworks. Like, are you going to review through the homeworks at the end, or like the audience should take the note of homeworks while they're lecturing?
What I can do is just send it after the session is over. I don't want to spend time during the session, but after the session is over, okay, I'll share the notebook and I'll point out, I'll write that in, what the issue is and how you can try to solve it. All the data is available, and it's pretty tiny and compact, so I think that anybody can actually do it. And then we can review it maybe in the next session. How's that?
Very good.
Okay. All right. So basically, this is now the real world situation. Is we got this actual, these are mobile application crash types. These are session numbers. These really are screens, events, and services. Of course, everything is masked. The proprietary data is masked. And this is what an actual, in my day-to-day work, what an actual query would look like to convert these. And basically, we wanted to know, because we want to do some sort of like graph layout. Where are these things happening? In the beginning of the session, or the end of the session, or what? So for example, there's some particular, so one thing might be like the sign-on screen. Here it's mask number 3, but the sign-on screen pretty much happens at the beginning of a session, right? However, some other screens, people can navigate, or users can navigate anywhere in a session, and this is averaged over thousands of sessions, and you can see that some of them can occur anywhere in a session. And of course, we can use this to rank order, and we can do the exposition of the graph, of the flow graph. essentially using this sort of information. Okay, so I'm not going to go through this entire thing, but you can see that it's extremely similar to what to the toy example that we just did. Okay, so even though this is toy data that we used, you basically build up in sort of like, you know, with slightly more effort because there's more levels involved. You can essentially do real work with exactly the same kind of principles involved. Okay, so this is pretty much concludes here. I think I'm going to take 15 minutes to do some more work with the FICO. So it was the FICO machine learning challenge. So if you remember, so let's go back here. I have this partially in memory. I don't have the entire thing in memory, but it's enough to do some live coding here. So let me clean up my screen here. So if you remember, the idea here was that we have something like 10,000 accounts. You have 24 columns of numerical information, and then you have a label, which is good and bad, meaning the accounts are bad risks or good risks financially. Should you give them a loan? And then to make it explainable. So really don't use neural networks because the neural networks are distributed, very difficult to figure out what weights are carrying what type of information if you get audited. So then, you know, basically the internal teams and also the regulators, as well as the clients, have to know what's going on and how did you come up with the decision to turn down somebody for a loan. So this is very real world application, okay? All right, so I think the last time we did a lot of the cleanup and sort of like structure of the data, and I think I can begin with, let's see, the empirical CDF. So I'd like to do some live coding here. So if you remember, like I tend to, when the data becomes very complicated, you sort of have to give sort of markers. And, you know, sometimes for some projects, I have markers that are like chapter numbers. Like in my book, I'm going to use like chapters as the, you know, chapter 1, chapter 2, meaning the stages of the data. Here I have basically something called head, again, going by the Git analogy. Impute prior predictor mean. So this is actually a little bit difficult because group account by risk class. You know, because I have so many things in memory now that just using this head as the last one, this is probably incorrect. So I probably just want to go by here. Let's see here. I bet you this is going to be here. I'm going to show you what the results of this query is because I made it in memory. And it's basically these graphics. Sorry, these are the internal information this is the internal information that you can use to generate the graphics. And here's how it works. So for example, let's drill down on one of them. There are 3 branches in the data here. Let's just go down the bad. These are all the bad accounts. And I have 3 branches. Notice that I have the bad accounts, the good accounts, and also both. And because the reason is sometimes it's a lot more convenient to just have like everything grouped into one instead of going into both branches and then having to combine them. So now what this information is essentially doing is that you have, for each one of the predictors, and again, remember, we have 24 numerical predictors here, we have a function that we can use to map these. To map this to individual, let's see here. Essentially, this is what we're going to be shooting for. We're going to be shooting for this, and I'm actually going to be combining. So actually, it's here. Like, let me back up my statement and just go to the original situation here. So the idea is that you can use these internal data distributions, which are empirical distributions of data, within the framework of the data sets, and also you don't have to use data sets again. Like if we normalize everything, these are just structured associations where you have nested associations. Again, at the top level, you have the good, bad, and both. At the second level here, you have the predictor. And then underneath that, there's an actual function. So we don't have the data anymore here. We just have a CDF that represents the data. And this allows us to basically skin it and do things like whether you want to use the empirical data, which are just non-smoothed data sets, essentially, or probability distributions. But you can also smooth them with various kernels. And you know that makes a difference, right? And then, of course, by choosing the kernels, you can choose a different distributions. So let me not use head. Let me just go directly with this particular. Yep.
Can you please comment on the axes on this data? What is the x-axis and what is the y-axis?
Yes. Okay. So to get this probability distribution query, essentially these are the normalized scores. So if you remember, let's see if I can back up here. the original data that is given to you, this is extremely common in data science. You're given data that is not given to you in normalized form, and you normalize it. We did this in the first session. Essentially, if you remember I wish I had a separate notebook with just I really don't like scrolling up and down here. By the way, I have an idea for essentially a remote control that would be like an iPad, where you can index your notebooks when it's so big, and you just have headers, and then on the iPad, you basically click to go to the different sections, because otherwise you end up scrolling all day long. In any case, this is what the original scores are not normalized. Okay, so external risk estimate might be 0 to 100, but then this column, this other predictor might be months since the most recent trade, and that's like number of months, right? It's an actual natural measure. So this might go from 0 to 24 months or whatever it is. So these are completely off, they're unrelated metrics. So one of the first things you have to do, and we did this last time, was that you have to normalize them and even flip the polarity, because some of them are, the higher the score, the worse the risk, and some of them are the opposite. So you have to actually normalize them and also flip the polarity. So how we did this essentially, and again, you might want to review the video. I'm not going to go through this again, but we scaled everything from 0 to 1, and that's what you saw in the, going back to the graphics. So the x-axis is basically 0 to 1. It's the normalized score. And for some of these, they have to be flipped. They're not flipped yet, but some of them that you see the asterisks, let's see if they're here. If you see any of the names that have an asterisk after them, they're flipped, and there's a data dictionary that essentially allows you to flip them. But basically, the 1 becomes a 0, and the 0 becomes a 1. So essentially, let's see here. Do I have anything that's negative? There shouldn't be any negative data here at all. It should have, everything should go from 0 to 1. And there's something, basically, I'd have to modify my graphics function, which is made really for correlations to show that. But basically, everything goes from 0 to 1. Okay, once it's normalized, and that's essentially the data that we deal with in building the classifier. So coming back to this, let's take it back to here. So how do these work? Essentially, each one of these is a function that is callable. So if I go, let's say, down the branch of both, and then ERE. Remember, these are nested. So now I can essentially, so now I have a single function. So now with a single function, I can basically call it, right? So now if you have, it's going to output a particular value associated, and that value is driven by the data that we collected. How you actually generate it, I believe that, let's see, how do we do it? You use empirical distribution. This is really neither here nor there. Essentially, what you do is you get rid of the, I believe, the account numbers. Get rid of the account numbers and basically do a merge. You have to be careful about some of these things like delete missing. If you have missing values, then some of these subsequent functions will not work correctly. So you first have to strip any missing data here. Quiet, because there's probably some other, it doesn't, data set has some issues when there are warnings that pop up, you might fail. And by trial and error, I realize that you can use quiet to suppress some of these. Maybe in another, if there's enough demand, I can get into some of you do this, but these are pretty straightforward operations, essentially. It's just a merge. You can do the same thing. So now, by using empirical distribution, you get these, essentially, they're all staircase functions. But if you use smooth kernel distributions, you specify a bandwidth, and you get these other things down in here. I might as well show you. You can see that these are staircases. They might not appear as staircases simply because there are a lot of values. Okay, but basically, the smoother ones look like this. So, one of the large lessons for data is that as soon as you have these sort of estimators, which are these smooth kernel estimators, you change the nature of the data. Look how different these kernel estimators are simply by varying the bandwidth from 0.1 to 0.02. So again, just to answer Matt's question, all these go from 0 to 1 because they're basically the values of the normalized predictor value. Okay, so now we've grouped the accounts into good, bad, and both. And now we're essentially throwing the data set and computing with all of them. So this is how it works. So let's say you essentially create something like this. We have a range that goes from 0 to 1 in steps of 0, let's say 1. Okay, and now we just simply throw association map. And again, association map has 2 modes, but the mode that we use here is essentially taking the original point and then using that as the key, and now you can throw that here. So you can see that you can use it here, right? Now we're going to substitute it here. Again, in most other languages, you cannot even do this. You cannot even throw some generic f. You first have to define the f. In Python, you would have to. This would throw an error. What is f? The interpreter doesn't know. You'd have to do this ahead of time. But how convenient is it that you can just do this? Because that's all you wanted to know is like, where does the f being applied and how? I think this is really incredibly convenient for data science. All right, so now that we applied this, I believe that this works as an operator. Yeah, okay, we don't even, you could also do this, but it's there's no point in doing this, right? You can also call it as a function, essentially, but basically, this gets you this. So essentially, now we have an association that for each account, I can say, well, from the value 0 to 1, what is the, what are these accounts? What are the values of the distributions? So now, going back, let's do what we actually did, because this is actually using, this data is the input. Where did it go? Recall, this data is what's given to us, right? For each one of these predictors, for example, if I wanted to draw this particular thing here, there's 3 things that I'm doing. There's the both branch, and each one of the both branches, the ERE, MO2, and blah, 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 and so on. But then, of course, the good data and the bad data also have them, and this is the nature of 3 curves here that we have, right? So this plot distribution query function is really what's doing a lot of the work. And I have to be honest, I'm not entirely happy by the length of this. Anything that's more than 3 lines long for me is a pain in the ass, and I would have to probably find some way to refactor this in a way that it becomes easier to do. But this step that I just showed you, where you generate the association, that's here. So that's the first thing you do. You basically go into all the 3 branches, good, bad, both. You go into all the branches that are like the, each individual predictor. So that's level 2. And then you perform this. So let's see if this works, actually. If I take this, let's do some live coding. If I go into the 1, actually, by the way, if you just do 1, you just get the data for the branch. But if you wrap this in parentheses, you get the key as well as the value. So this is very convenient, right, for actually displaying this. Okay, so let's just apply this association map. Let's just do it. I'm going to just fix this to 0.01. Actually, 0.1. It doesn't matter what it is. Okay. All right. So now for each one of the branches, basically we created this. So now for all, so let's look at more branches of. So you can see that if that's all. Of course, again, you will be actually developing in one branch probably. And there's something that me and Mitch discuss all the time when we do this. This is so convenient. And then you just go here and just say, well, how does it work for all of them? And then of course you still have this higher level here where you just want to create for all of them. And now let's just get rid of the normalization for a second. So if it worked in one branch, you might still get some problems when you're dealing with the other branches. Maybe missing values is the typical error. But yeah, you can see that you have three branches here. Let's scroll up and down, actually. I got some flack last time for not using the transport control here on the data set. So this is the both branch, and if you drill down or move down, the problem is data set is not very responsive. So you can see that it took a while just to get to the bad branch, but essentially all three branches are available. And for all three branches, we did this association map for each one of the predictors. So now next, what's going to happen is this query transpose. Transpose is very powerful. It's essentially, transpose is very similar to values merge with something similar to this, okay? I'm going to put this in quote, or let's make it into like a thing, transpose. But if you want a mnemonic, it's very similar to this sort of pattern here, okay? So if we do like query transpose, let's see, what do we do? We did this closes this query here. So if we do this query, let's see if just transpose by itself works. Transpose has some issues as well with the operator form of it. But now essentially, what are we transposing? It's the first two levels. In other words, the good and the bad. So now, did that work? No, I don't think that works. So let me try this. There are some issues that we're still trying to work out with the operator form. Wait, that didn't. It didn't seem to have actually worked here. Let me try one more thing, actually, okay? Sometimes you get this that works. Oh, I know what the problem is, actually. Sorry about that. I think that, let me try this. You see, this query is actually a definition of a query, right? I'm actually setting this entire bit of code, including the width and everything, and I'm using that, I'm giving it a name. And then when I use it in here, I'm actually calling it, and look at how this is called. This is pipeline, but it's not using the composition operator. And there's actually, so it's a little bit subtle, but I hope that this actually gets fixed in future revision of the language. But basically, we don't want to pipeline it. We just want to act on it. Let's see if this works here. Yeah, okay, so that's better. So, okay, so again, because this is actually acting on the data, you should actually work directly on here. So in other words, you cannot use the composition operator, but I bet this works. If you just post, yeah, see, so that works. So it's not composition, but if this head was not here and you define this as a query, then you can actually use composition and then define this entire thing as a query, my query essentially. Okay, I hope that people get the distinction. So essentially, you have one query followed by this query. However, since we had let's go back to the original thing that we had here. So we had the actual, we're acting on the data itself. So everything that happens here is acting on this data. So what we really wanted is this transpose that just essentially is piped after the rest of this subquery here. So what's that? So let's drill down on it. So now if I go into the ERE branch, okay, now you can see that you have good, bad, and good. So originally these were on level 1, and now they're on level 2 underneath here. Let's just make it a little bit more explicit. And again, we constantly have to fight this issue with data sets formatting rules. They're kind of ad hoc, but you notice here that now the things are transposed, right? And so this is extremely powerful when you want to try to merge things, because what happens next after this section is this sort of complicated-ish query. Let's try it. Let's just try it let's try our luck here. All right, so if I want to go down, let's go down to, let me take the first 3 levels here. Oops, sorry, I'm working on the wrong one. Let me delete this. Let's back out of here. So we wanted the transpose, and now we're going to go into this all branch here. So this all branch looks like this. So it's all the predictors are at level 1. And now this part of it, the key value replace, this is acting, you notice, at level 2. So it's actually after this. So again, let's use framed to get a sense of where this is going. And again, very nice to be able to do this. I challenge you to do this in most other languages. You're not going to be able to. So, right. So now this key value replace is one of my functions, I believe. So let me see what this is. Key value replace. Okay, so it's basically key value map. So let's just do this. Let me just try it. So key value map, let's just use it directly. Key value map. If you attempt this and to wrap an F around this, you notice that the key value replace is actually using patterns. It's saying essentially, take this pair, which is the risk class and the data. Here we have the first component, which is both. That's the risk class. And then we have the actual data that follows it. However, it's not wrapped in a list yet. And you cannot replace that directly. So what I do typically, I think it's a common pattern, I just map list on them. So now, there you go, there's your list right there. So now you can use this and replace. Otherwise, I don't know how to use replace directly through here. And I love replace because you have these patterns that are named, components of the patterns that are named. So to me, it's much better than using map index or these sort of things with slots in them. Okay, so basically, you're using list first, and then of course you can just compose. So if I compose now, let's just use framed again. So what's happening here, now you've got these 2 components, and what I'm doing is essentially throwing this dictionary at it. So let's see what these look like. So these dictionaries look like this. Believe that, okay, so let's just go to the risk class both, for instance. Okay, essentially just picking out the color, okay? So this is, again, this is a very easy way to sort of create both the legend and to actually use the legend as a functional component, because you're essentially, of course, don't forget to normalize it, because if you use this directly as a data set, this can get you into trouble, actually. So you have to essentially normalize this. and it's an association, of course, right? So you're going to replace the first component and make it into a color, essentially, right? So let's just try that. And you can see that this is basically this is what I mean by the language being orthogonal. All these features here, like risk and replace, let's see, data. This was in the language from day one, right? This is nothing new, and it works so beautifully with the rest of the language. Whereas, for instance, in Python, when pandas comes out, pandas has its own set of functions, and not all the functions in pandas work with Python, and not all functions in Python work with pandas. Whereas this is so nice to be able to just essentially reuse everything that you've learned in the language. So even though Wolfram language has the, so let me just do this real quick. So if you have normal dictionary, if you, the language, the Wolfram language has this reputation for having a high learning curve, which in many cases it does, of course, because it's very powerful. Just do it here. I'm just going to wrap it here. But on the other hand, you can reuse all these things, yeah? So you can just have, let's see, that. And if you have risk, I believe you should just get the colors. Oops, I think it's one deep. Risk data, one went wrong here. Let's see here. Okay, risk class colors. Somehow it's not even seeing this as this. Oh, of course. I think because the dictionary itself takes this class as a second component, I believe. Once it's normalized. So let me try this actually. Let me get rid of the normal just to show people. So again, I want to stress that this part of it is nothing new. This has basically been pre-existing in the language all the time, right? But if you add it, so let's try this. Does this work? How come this is not working here? So somehow this is not. I wonder if I made a mistake here. You know what? We can why don't we just quit here, because this is like we're already like 50 minutes into it.
Yep.
But I promise I'll essentially write this down. Why this is the problem with doing the live coding. Essentially, all you miss is a comma in the wrong place, and you don't get the right thing. I could have just copied this entire thing, of course, right? But of course, this works because I used it here this morning. Okay, so why don't we quit here and just go to like question and answer session for like 10 minutes or so. But
so one thing is that remember about the homeworks, that's one comment. The other comment, it's just a general comment from our beginner users. When you're working with the operators, it seems that you have a preference for right composition.
Yep.
Is there any reason for that, or is just your personal preference compared to, for example, postfix and etc.?
Okay, there yes or no. The no is that you don't have to do left to right. You can do, excuse me, I write like English, right? When you do something like F composed with G, composed with H, you also have the option of doing H, and I believe the syntax, I never use it personally. I think it's something like this, the star. I'd have to look it up actually, but there's basically a left composition operator, and you can essentially just do this, I think, F, right? So you have the option of going backwards, and some people prefer that. However, what I do like about it is that you're essentially going in one direction. There's nothing worse than having to backtrack and put some things in front and some things behind to essentially go back and forth. So, I think it's very natural in most natural languages to write in one direction. So when I mentioned this at one Wolfram conference when people said, well, what about in Arabic? You write from right to left. Or what about, Japanese, you write top to bottom or something like that. Yeah, okay, that's fine. You can try it. But the point is, it's all in one direction. You very rarely have to stop in the middle of a sentence, put parentheses around things, and then sort of like back up and go back and add things at the beginning of that. So that's what I'm trying to avoid, because then when you read it, it becomes much more natural to essentially like the eye follows the essential linear pattern.
So do you agree, in our audience, if they want to read their codes, they have to start from the right, whenever you're using right composition, because that's basically most of the time the way that you're writing your codes, right? Do we agree?
It mimics English, essentially. You've noticed that essentially I say, the first thing that happens is list. And then the second thing that happens is replace rules. Now, you have to be careful when you have multi-level queries, because in that case, some things actually get done, they get executed out of order in which you think that they do, right? If you sort at one level and then you do group by at the first level, the descending and ascending operators behave in different ways and they rearrange the order. So you do have to be careful about that. But I think that this, everything that I've showed you here essentially sort of, bolsters that point, is when you write and when you read it, you're more or less going from left to right. And if you know how to group correctly, meaning with these kind of subqueries, then essentially you can still have that behavior where you say, this is what I'm going to do. This is the first subquery. This is the second subquery. This is the third subquery, and so on.
And very quick, the other question is about normalizing the data. You mentioned it very briefly, during your lecture. Do you have any general comment, when people start working with the actual data? So what is the normalization process?
Yeah, no, you can refer back to, I believe that the first session we covered that in more depth. But essentially, it's a linear map, right? It's an affine transformation that, it takes these numbers and you apply a function to each one of these numbers. So you have a function that essentially looks at the minimum and maximum of the range. So in other words, the range of these. So you do have to fetch the range. Let's see if I can actually find it here, because I do have rescale predictors, essentially. So let me see, value trial, query x, performance, rescale min max. So this function, rescale min max, I believe it's another one in my toolkit, but it should be in the language, really, right? So you essentially, you always have to be careful about missing values and things of that nature, right? So you kind of do this delete missing things. But this is min-max is in the language. So you're basically saying, take the minimum and maximum. And by the way, you notice that this function, as in the toy example with the sessions, I do this very common pattern, which is identity, and then you do something, meaning that this is your original data, and then you do something to the data. So this data gets passed forward. This portion of it computes the minimum and maximum after you delete the missing values. And then again, there's something which, again, I think I'm trying to stress. You do this replace, and in the replace, now you're saying, take the data. I already computed the minimum and maximum, and now you do a function on it that rescales it. So the reason why I do replace rather than function is, again, because sometimes you don't have numbers. Sometimes you get data that is not clean. But anything that is a number, you essentially are applying this function to it. So it's x minus the minimum. This is standard, basic stuff here. But yeah, so this is the query that essentially can do this. And again, I would focus on this pattern here that tells you that you basically fork the data, and one branch of this fork just computes the range, and then you recombine them and by essentially applying that, because you do have to know this minimum and maximum range. Once you do this, essentially, you're mapping, and you're now going to be applying that to each individual number, right? So you start off with the raw data, and then if you can compare this. So again, this notebook is available on the Wolfram data repository, so anybody can actually play around with it. So if you go to the rescale predictor branch, let me just inspect it real quick. Let's see here. Let's just look at it. This is another thing that you have to be mindful of when we do a live coding session. Even though this is in memory, yeah, sometimes these are very large. Maybe you can, and there are issues with trying to abort the evaluation as well. I would love to slice down on it, but in any case, let's talk through it while this hopefully it renders. Instead of the original numbers, you get these sorts of things here, right? Basically, everything is mapped 0 to 1. So really, the important part is this particular function here that actually that identifies the range and essentially rescales it. Then there's a second procedure, which is, sorry, so everything is frozen apparently because I cannot even switch from one to the other for some reason. Let's see if I can do this. Yeah, sorry, don't ask me why. This is not even a very large data set, but sometimes it gets into these funky sort of thing. You see that it only took 7 seconds to make this, but it's one of the challenges. If this were a bare association rather than a data set, this would not be happening. So it's strictly because of the type system and just glitches inside of a data set. And I cannot even, I don't think I can even abort it. But yeah, so you would find, basically, once you do this on your own and you just inspect this, you will see that essentially these scale predictors, are, instead of being from 1 to 55 or 10 to, there you go, it's rendering. Well, not much data there is there. They all essentially line up as 0 to 1. Then the subsequent operation to this is flipping certain of the predictors. You have to essentially do another operation that is another refined transformation, linear, that basically takes, it's 1 minus x, I believe. Basically, it's something as simple as that. But you have to know which level to apply them in. So yeah, you end up pretty much every data problem that is like a classification or regression type of challenge, you have to do this normalization. Excuse me, I shouldn't even say that. Sometimes you can use linear algebra, and the linear algebra kind of takes care of these axes for you, tells you which ones are important, even though you didn't do the normalization. But yeah, but this is it's a nice way to sort of like put everything in the same unit of measurement, essentially. Yep.
Excellent. So let's see if there's any other question from our audience. So if not, I'll go ahead and I'll ask one question. I noticed you're using, different, predictors and estimators. How sensitive are your data to your predictors? If you choose a different number, a different value, would you get a different result? For example, would it happen that, one of the bad results becomes good result and vice versa?
Yeah, and hopefully we'll get into it. We didn't get to cover much ground here, but towards the end of this notebook, I actually do this in a couple of different ways. You can rank order using there's several approaches, okay? But if you remember the graphics that I showed you, it's really too bad that I can't even scroll down here. But the graphics with the red and the blue and the green, the gray stripe curves, you can use those to essentially, right off the bat, rank order the predictors based on how much they separate the data. In other words, there's a cluster of the good accounts. They're going to be that perhaps, for external risk estimate, if you look at the good and bad, you can see that the bad accounts are sort of clustered around 0.6, and the bad accounts are, and the good accounts are clustered around a higher value. And if you look at the distribution, that's basically what those CDF curves actually tell you, right? So that's a pretty decent separation between the good and bad accounts. So you can actually measure that and rank, and in fact, I do that later in the notebook. I rank order these estimators based on their separation using the CDF. So in other words, using the probability mass distribution, you can actually rank order. But that's just one way of doing it. And in fact, later, when you create the classifiers, then you measure what's called the area under the curve, which is essentially a measure of the classification performance. And using that's a slightly different, it is a different way of doing it. And then following that, I compute, if you have I think unfortunately this is completely kaput, but basically I will show that there's a correlation between doing it this way, rank ordering by what's called the separation, and using the AUC metric. So they tell you typically similar things, but for some of the predictors, they're actually pretty different. So that's, I think, is what's interesting about it. So ideally, we will cover this in the third session. We'll have to find some way to sort of prevent these kinds of problems with data set in a live coding type of scenario. But basically, yes, these questions will be answered when we finish this, by the time we finish the notebook.
Excellent. So I believe that's a very good time to wrap up our second session, Live Coding with Data Science. Thanks again, Alan. Thanks everyone for watching our live coding.
Thank you very much. I hope everybody enjoyed it. Sorry for the snafus here, but I'll correct them and share the notebooks with the corrections.
Awesome.
And the home.
Thanks, everyone.
Thank you.